Hey, Jawad. Hey, Rao. Hey, Rudy.
Hi, James.
Hey guys, James Chawad.
Hey, Tony.
Hello, guys. Hey, Rudy, welcome back.
Hey, thank you, Tony.
Sure.
Just quickly share my screen here. I think from the first meeting we had last week. Yeah, I think Tony, David, Kendall, Jen, and I was there, and we discussed a bit about the areas, and Jen was agree, I think, to present the BUM rules and general test cases. So I assume Jen will be joining, right, Tony?
Yes. Yeah, he's presenting today, so I hope he'll be joining us.
Yes. Is Kendall will be joining again also today?
I don't know. Can you check to see who responded to the invite, David? I did talk to Mike Walsh and Mike Lafferty, and they said they would be dialing in. They might be a little late.
Okay. Yeah, I saw Kendall check he's attending today on the calendar invite.
Okay, let me ping him. And I did talk to Mike earlier today. He said he would be dialing in, but he said he had 3 other conflicts, but he will make sure he's on at least part of the call.
Okay. Right, Jen is here. Hey, Jen.
Hey, good afternoon.
Good afternoon.
Hello.
I think Tony, we will have a soft start last week, right? Last time, not last week, 2 weeks ago. I think we have actually more complete people this time. Maybe you want to go ahead again, introduce briefly before we start the meeting with Jen.
Zane?
Yeah.
Oh yeah, I mean, Tony, you want to maybe go again to do some introduction? We have more complete people this time. Right? Last time we only had a few people, right? We didn't. People didn't know it was started. Yeah.
Right. So you want to do a roundtable or?
Oh no, maybe you want to give an introduction about this meeting right? About this ATK. Last time we had 4 people.
What we're doing. Oh, okay.
Yes.
So just as a reminder for everybody involved and for those new, this is an initiative that we're starting in OCP to define assembly design kits, and there's a lot of things associated with assembly design kits. I think Zane is going to get into his view of what needs to be covered, which I've looked at that and I think it is pretty well aligned. So initially we're going to focus on common assembly design rules, developing a format to describe those rules. So this would be, how the bumps and micro bumps are placed within the die, and how they get interconnect and the rules associated with that. And then we do need to talk about assembly, 3D stack. There are some current standards being driven by TSMC with their 3D blocks. But that is something that we may consider also, as part of the overall plot process. So defining the die chiplets, how they get stacked up with the package, as well as all of the rules associated in defining that connectivity. There's another initiative to try to standardize on MDKs. So if anybody's material design kits, so anybody who's interested in participating in those discussions, we meet on the alternate Thursday at this time slot. So we have 2 initiatives right now, ADKs and MDKs. And you're welcome to participate in both, but if you're more specifically interested in one area, you can do one or the other. Any questions or comments? Is Kendall on the call?
Yeah, I saw him here.
Okay.
I'm here. Yep.
Okay.
Hi.
Hey, Kendall.
Should I start, Tony?
You can Kendall.
Yeah.
Let me share my.
Yeah, go ahead. Yeah, go share screen.
Yeah. Just I think everybody knows Kendall, or I'm sorry, Zane. But Zane, maybe just a quick intro for those who might not know who you are.
Okay. Hey, everybody. My name is Zane, and I'm a IC packaging application engineer working with Intel's TD group, and I'm part of the ADTS team, and we develop flows for all of our packaging and assembly test chips. So let me share my screen. Right. Let me know if you can see.
Yep.
Okay. So just before I get started, just a quick disclaimer. So this is not a formal proposal. This is just a quick overview on the die definitions and the subsequent collaterals, and then just kind of providing what we're thinking and what we need. And then just the final die and assembly rules proposal will be shared in the future. So just there's a couple of things, right? So there's going to be like some discussion on what's the format, what the rule format is, what the the encoding is, and all that. So all of that can be decided in the future. This is just like some of the items that we're going through right now as we're developing our die and assembly rules. And then just to kind of start out, right? The initial is the actual definition on how the die file is defined, and that comes in because how you define a die file will kind of like determine how you write the different rules for the different environments that you might run into, and I'll kind of go over that in a little bit. Okay. So just to start out, one of the initial main objective is to have an improved ASCII die file format. Currently, in Intel's context, we have something called a .die file. All it is just a text file that contains like bump information, so like XY locations, net names. If for example the bump needs to be probed, all different kinds of properties get added into this like text-based file. And one of the issues that we're running into is that the number of bumps that we're dealing with in our design is exploding. In the current die file format is not very modular, and it's failing in keeping up with the requirements for our designs. We want to use a common format standard, so I'll kind of review it quickly. I think we have talked to Siemens about it. Is just use YAML, but in the context of CDX, it doesn't really matter. But we would like to stick with a common format so that everybody can just use it. There needs to be logical parsing. So like our current die file is not very easy to read. So you really need to know what's in there to understand what's going on. But we would like to have it so that anybody can kind of open it, look at it, and then design their rules for whatever it is that they're trying to do. Then kind of like the next few items are going into the more details on how everything is linked together. And then this will determine how your rules are defined. So you would like to keep the object definition simple, and then everything needs to be extendable for new custom die properties and bump properties. And then it could include like fiducials, regions, and other objects. So obviously, Intel does a lot of different types of designs, but it doesn't cover 100% of what's going in the world. So the general kind of concept here is, as new designs are coming in or like new features are needed, we can extend it without like going through some like longer procedure. Like if we need something like fast, then we can just kind of extend it ourselves. And then the very final objective is to make sure that you can use it across multiple designs, domains, processes, and use models. So in that sense, right? Like we don't want to like have like different formats for like different processes. Like it can be extendable to whatever it is that you're trying to do. Okay. Any questions or comments here? Okay. And then moving forward, the notes on the optional parameters is that basically it's just kind of extending what I said in the previous slide, is that you would like to use it across like multiple design domains, processes, and use models. And it should be very modular. And then one of the main kind of ideas is currently, right, everything is done towards the end of the design. So for example, once your design is complete, then you will go do your mechanical analysis, your SIPI analysis, your thermal analysis. So what we want to hopefully accomplish is not be limited by a complete design. So as the different pieces of the design information come in, we should be able to kind of construct a model for early SIPI analysis or early thermal analysis. So depending on where your design lifecycle is, you should be able to kind of use that data in other domains. And then we still need the format to be like modular, so it can kind of store any information that may be needed. What Intel needs might not be required for other companies. So we don't want to, close the format down in any way. And then the minimum required parameters will be defined. Generally it's just bump XY locations, like the die size, some other basic parameters, maybe like net names if you're trying to run SIPI analysis. So the different tools that will use this format can define whatever minimum requirements that they have. Okay. Questions or comments here? Right. So the next one is kind of the advantages of using this new format versus our existing die format. So once again, this is a little bit more in the context of Intel designs. And then we would like to have mapping sequences and data hierarchy. You can kind of like enable and disable sections as you need. So as we mentioned, or as I mentioned earlier, our designs are exploding in their size. So it's just like hard to parse through all the information. Maybe like 10 years ago or something, you could probably just look at a design and figure out what was going on. If you were in the thousands of bumps or tens of thousands of bumps, it was still manageable via Excel or just maybe even manually looking at it. But as you start going into millions, tens or hundreds of millions of bumps, it becomes very hard to just manage data. And then, as I mentioned, the proposed format for us is YAML, but it could be anything. It doesn't really matter. And then we would also like to start by defining some simple cells on multiple layers. So this could be like, once again, modular. So if you want to have polygons on multiple layers for your design, you can. Generally, we have fiducials that are used for alignment. And now, with the larger BumpCon designs, we have a lot of fiducials. So this is something that we would like to extend to this format. And then the last kind of point is, as we are going into more die stacking or 3D IC definitions, like a better way to handle the front side, back side bumps. So this has, I think, everybody kind of uses like their own little definition. But we would like a better definition for this, and all of this will tie back to the power via definition, which is just basically getting power delivery to the backside bumps. And then just have a better way of handling bumps that are on the top and the bottom of the die. And then the last piece is track the data transformations between domains. So for example, when you design a die file, you'll have you'll be doing it like on a silicon tool. You start laying it down your transistors, and the bumps are on the top. When you go back to your package domain, you'll flip it. So just need to make sure that the data transformations are being correctly handled. Okay. So coming to this, hopefully we can have a little bit comments or input from some of the other folks on here. So I set a baseline for the the die file format, and then it kind of comes into going into the target usage, and then we want to be able to use this in any kind of design domain. And so starting out, so the first thing we would like to do is support co-design, so silicon to package or 3D IC stackups. So basically making sure that like, let's say for example in the silicon to package definition, right? If we define a die file and we have like a package definition available, maybe we can run like early thermal analysis without actually having like a fully routed design. Or maybe we can do some like early path finding if there's like multiple chiplets, just to make sure everything will fit and it will meet the power requirements. So that would be like usage number one, is focus on the co-design part. The second one is going into more DRCs. So actually running like the physical DRC checks on the silicon itself. Make sure the bumps are correct. The bump density is correct. The power to ground ratio or signal to ground ratio or diff pairs or whatever the DRC rules are. Those can be easily supported. And then the last part of it, hopefully some of the other folks can comment. So I'm not an expert on the sort test design or the wafer processing side, but generally our existing format supports sort and wafer processing in some capacity, and we would like to also see that whatever the new format is also supports it. So
you're talking about wafer sort, probe pads
yes.
for wafer sort?
Yes. So
okay.
I think we'll kind of define a little bit more in the proposal when it comes through, but that will be the general idea.
And what's the idea of sort DRCs?
So this I'll I'll have to come back on this. I'm not an expert on the sort DRCs, but there are some properties that we add inside our existing die file that is used by the sort team. So I'll have to follow up on the sort DRC part.
Okay, so this is wafer. This is wafer sort.
Correct. It's on.
DRCs.
Yeah.
Oh, I thought you meant sort design rule checks, but you're talking about wafer sort
Yeah.
DRCs. Gotcha.
So Tony, my thought is that the probe cards will define the let's say physical spacing or dimensions of associated probe paths. So they may have above and beyond design rules than what the foundry can or the 3D-HI assembly can do. We'll get there.
Yeah. Does everybody know what a wafer sort and probe card is?
Yeah,
Does
I'd like to
anybody-
NOS,
Does,
I'd like
does
to see
anybody
us. Yeah, go ahead.
does anybody not know what a wafer sort probe card is?
I don't know.
Okay. Yeah, just without getting into a lot of details. So you know, when you get a wafer, and typically you're going to want to test the die on the wafer before you cut them up and put them in a package. So in order to be able to test the part, you need to you know, get access to the die, so all the primary I/O, but you also need to power up the die. So you know, with traditional flip chip, you can access a C4 bump directly with the probe card, but when you get into these fine feature things like for 2.5D and 3D, you can't physically probe those micro bumps. They're too small. So generally, what they do is they create larger pads that are used just for testing. So sometimes they're called sacrificial pads, or you know, probe pads, and you know, the probe card will have mechanical probes that connect to all of those pins, and then that goes out, allows you to test the part. So you have to power it up and test it, and then if it's good, you pass it on for packaging. If it's bad, you mark it as a bad die, and you don't assemble it. So that's kind of what they are. So you know, that it's put into the database. Sometimes that can actually be done by post-processing the wafer, and I've seen that technique used for 3D, where you actually build up another stack up on top of the wafer so you can test it, and then you strip that away. But for typical probe cards, they're built into the actual layout. So you need to know where they are, and you know, have pin names and identified in the database. So that's part of the planning process, so you can support testing those at wafer sort. So we want to be able to somehow, you know, the format should, and I agree, should be able to support, you know, defining these probe cards where they're at, and you know, the electrical names of those pins.
Yep.
Okay.
Like one example I can think from the top of my head is like wire bond, right? So I don't think I've seen wire bond in my time here at Intel. You know, maybe some teams are doing it, but if that is something that, you know, some of the other folks on here would like to see, right? Then you have to see how those will be supported in terms of like your DRC checks, or making sure it's getting aligned with the package properly, or on the co-design side, make sure that it's being done correctly. I think I've seen some presentations in different forums on the wire bond side of things from Micron.
Yeah.
Yeah.
Zane, I think we did talk about that in some of the earlier MDK or 80K discussions, and I think we said it, at least initially, we want to focus on 3D IC, and wire bond doesn't really, you know, there's systems in place that handle that, and I don't think we're going to see bleeding edge chips using wire bond for traditional packaging. But
Okay.
having said that, you know, when you start getting into optics and lasers and stuff, sometimes you may need to do some type of wire bonding. So I don't think we want to preclude that for maybe some types of special technologies. But I think the initial focus is let's focus initially on 2D and 3D.
Okay.
But I think we should just, we don't want to box ourselves out of that. But right now, the initial focus is 2.5D and 3D. Anybody else want to comment on that?
Yeah, I think that's right. So wire bonding still is the main technology in many applications. So format needs to support it.
So are you saying that, Joe, are you saying it should be a priority or not a priority? Because Tony, I think we talked about last time, should not be a priority for wire bonding.
Well,
Joe,
yeah, long term, I think, but short term, I think it's less of a priority. I mean, Jawad,
Yeah, so the thing is, it's a very well-established technology. And if you look at the LPDDR die stacks, they're all for foreseeable future will be done with wire bonding. So how does that play into chiplet integration is to be seen. I would say it's not a priority, but we have to have a mechanism in the format to handle it.
Yeah, so
I
we
agree
don't.
with that. Tony, we do have an example of 3D stack with wire bonding as well.
Yeah, I am familiar with that one. Yep.
Yeah, and some of the through module via stuff that scans or circumvents interposers could be considered wire bondage. So again, I think wire bondage to how we handle those is pretty similar in its nature. So, and then I would add probe card design in a traditional sense, but then when we're talking RF is maybe more membrane and bumped probe cards as options there as well. So.
Yeah, and by the way, Rudy is from Cadence, and he's our RF expert on the team, so he's going to keep us honest to make sure.
That is a RF expert, yeah. Still, high speed interconnect, yeah.
Yep. Yeah. So those are things we need to support. So whatever we do, we don't want to preclude wire bonding and also even on the die side, Rudy, I talked to Michael or Lafferty earlier, and anything we need to do special to support, connectivity rules or even die definitions for the stack die is important.
Yes.
Okay. I need to step out for 1 minute. Somebody's at the door. I'll be right back.
So basically, I think just kind of summarizing the approach that we're taking, right? So if something is not included in our proposal, if the end user wants to add it in somehow, they can temporarily add it in using some kind of modular definition, and then in the long run, it can be supported as like an official part of the specs here. But these are like the 4 kind of areas that we're targeting to check. So as we define our die, we want to make sure that the assembly DRCs and stuff that we will have cover these use cases.
And again, just to cover again, Tony said that, but the SWOT DRCs are more physically based. You're not talking or referring anything to do with like fusing or electrical fusing or anything like that. Those are purely physical based type rules, correct?
Correct. Yes.
All right. Thank you.
Yeah. Like in the context of what we do specifically, like as I mentioned, right? So it would be something like, let's say you want to check bump spacing. So I'm gonna make sure like all the pitches are, I don't know, like 200 or something, and then some areas like might require like higher pitch or something because you might have some critical signals in there. you can't break out easily. So that kind of goes back to defining regions. Make sure that in that specific region of your die, you can have more flexibility, or I guess have a different rule just for that specific area. So how we define the die will kind of define how you can set up the different rules and stuff, right?
So Zane, do you have kind of a crystal ball that determines how many pins we need to deal with for die definition?
So I can probably say like tens of millions of pins soon. That would be like our target in the next year or so, going up to maybe like hundreds of millions of pins.
Yeah. So we're talking about a lot of pins. So just doing a brute force, ASCII file for a flat 10 million pins is probably going to be problematic.
Right.
Is that a fair statement? So, so is that the idea where you would kind of have repeated structures and define them hierarchically?
Correct. Yes.
Okay. So James, a quick question on the CDMXL format that we did for the parts model. Did we do we have the ability to do kind of hierarchical definitions of the mechanical model?
Yes, we did discuss that, I think, as part of the integration with the JDEC JEP30. So we did introduce the hierarchical that can be repeating in terms of the regional, I think, like the stem structure format can be reproduced in that way. Yeah, we can support. I think it probably can reuse that same format structure here and for the same purpose here.
Yeah. So so the CDMXL format is an Excel format, and that's part of the JEP30 standard, and it has a provision to describe a lot of information similar to this die, but we are limiting what's in JEP30 to be specifically more targeted for the integrating the die into a package, so it's information just related to the package. It doesn't know anything outside, what the stack up is. It's and the intent really is for a chiplet provider to provide, the pertinent information on the chiplets that a system integrator would use. So we could possibly use that format and extend it to make sure we support that, or if we decide we want to go YAML, I think it's probably would be pretty straightforward to be able to translate back and forth, I would think, right? So if we had, in our new format that we're defining here, we could probably create that JEP30 mechanical model. James, do you think that's...
Yeah, I think so, because they're both are structured, right? Definitely, I think they are way able to transform that between the XML and the YAML there.
Right.
So are you thinking about, like, we still stick it with the XML, but then we have an option to formatting it or transform it into a YAML to...
Well, the thing is, we don't necessarily, that standard's already out there, right? And it doesn't include a lot of the stuff that we're talking about here.
Yes.
And I don't think we want to extend this additional stuff that we're talking about here in the JEP30. So I just want to make sure. If we stuck with XML, then we could maybe have a subset of that. But I think I want to pick the best format. So I do want to have that discussion, and there's pros and cons of YAML versus XML. So I think you know, I'm leaning towards YAML because it's what 3D Blocks is using for TSMC, so it's more consistent with that, and it's just more readable. So the design engineers, I think, will be able to, you know, don't have to be XML experts to do that. I think it's a little bit more readable and easier for them to adapt. But if we are going to drive this with a JEDEC standard, we should have some discussions, and I will talk to Michael Durkin to make sure they don't have any issues with that. I know some issues that they brought up in the past is they don't want to have formats conflicting with any JEDEC standards. So there's a potential issue that we just need to have a discussion to make sure that we're not stepping on the JEP 30 you know, CDMXL mechanical model. So just want to put that out on the table. You know, we don't have to go that route, but I just want to make sure that there's nothing that we're doing here that's going to preclude us from being able to standardize this through JEDEC, which I think is the end goal here. So initially, in defining these formats, we want to have them open, machine readable, so that, you know, people have access to them. They can start prototyping, extending it. So this is really kind of an incubation center to drive these formats. But longer term, we do want them to be standards, but we don't want to wait for those to become industry standards, you know, blessed by the standard committees, because that's realistically at least a year or two away, and you know, we've got a job that needs to get done. So I think that's probably one of the main advantages of working through OCP. There's other routes that we could take this, but you know, if we wait for the standard to get out there before anybody can use it, I think the industry's moving too fast, so we can't go that route.
Yeah, that makes sense. I agree. Go ahead.
Yeah. So, you know, Mike Walsh, any comments on the YAML versus XML, or anybody else?
I do have.
The only thing I would say, Tony, is it's just much easier to work with. You know, you can use regular text editors. It's, you know, parsing is similar, but I don't know. I mean, I'm a supporter of a YAML just because it's, you know, you can bring it up in a notepad and it views easily, it collapses, it expands, and you can generally easier to read without all of the tags surrounding everything.
So easier to create and edit. What about parsing? Any disadvantages of that versus XML?
I don't think so. Not that I've seen so far.
Okay.
Yeah, I think one thing we should think about, you know, if we truly want to support 100 million IOs, then, you know, reading some of these dies with that type of description, you know, what would be better in terms of the computer algorithms?
And to be honest, you know, I was just doing a rough calculation, Tony and team. If we think about some of the 3DHI systems, you know, they definitely hit the reticle size, and DARPA is asking about 200 nanometer pitch. So we can assume that in our calculation for the density of the bond.
Well, I've seen even 100 nanometer people talking about, so.
Sure.
Yeah.
So we can even go 100 nanometer pitch in our calculation. And if you think about a full wafer scale integration, because that's where there will be, and you design a system at the wafer level now. So for a 200 millimeter wafer, you're talking about 250 billion such bonds, right? So.
Right. That's why I don't think a flat approach goes.
Just hierarchical is also not enough, and that's where Zen, you're leading to some thoughts there. So I think it's really important beyond hierarchical. How do we do this definition in an array format?
You start to need some of the concepts like the GDS has with array references and test references.
Right.
I don't know that there's another way to describe that many objects more efficiently than what GDS has been doing for 30 whatever years.
Oh, it's yeah, close to 40.
I think, Joe, I think that what you mentioned makes sense. So there's a couple of ways this is handled. We talked about hierarchical. We need to optimize how the data is represented to make it into a sane size. But at some point, even that data will become big. So the next step that's typically solved is that all that data is compiled into binary and stored as a binary format. So that think of it this way, right? A binary format will basically, whatever parser parses it and stores it in memory, it will do a memory dump. So next time when the parser needs to load it, it doesn't parse and load one item at a time, it loads the whole memory. And that's where the speed comes from. So I don't mind, we can consider 2 steps where we have a text format, and we have a specification of how that gets written into a binary format, and even a little code to store all of that, so that right with the library that writes it and reads it is all we need. And then anybody can link against that library.
Yeah, along the similar lines, David, encryption, right? Because I mean the format is open, but when you actually put the actual rules, you know, the ability to encrypt that, or at least have a binary file, is going to be important to you know, the foundries and a lot of vendors. They don't want that stuff open source, you know.
Yeah.
So
yeah.
I assume with the binary, you know, we could somehow have it in a key associated with that for protection.
Yeah, we can. I did some encryption sometime back, and I'm kind of suspicious of my paranoia kicks in, and I'm kind of suspicious of these encryption schemes, because you always will need a master key to decrypt that, and extracting that master key from a tool, although it's not easy for anybody to walk by and just extract it, it is doable. So a determined person can always extract whatever they want from whatever file they want. Right? They can always see the memory layout. They can see everything. Even after encrypting, the tool will have to decrypt it and store it somewhere in memory, and people can see that memory layout and all that stuff.
Yeah, but you know, we're not even showing that level of detail. So, you know, in order for somebody to reverse engineer the rules in the pitch, you know, from decrypting a binary file, you know, is a little bit different than some of the stuff DARPA is concerned with. We're actually reverse engineering the logic and you know, potentially tampering with it.
Yeah.
So I think, you know, we don't need the highest level of encryption, but we probably need to make it, you know, first level.
Yeah, I think the right word which you're looking for is obfuscation.
Yeah. Yep.
Yeah. One thing I want to put into consideration here, I think like the YAML, I think I would say XML is like the one thing I think like we all this I think I good about YAML. I think one thing I think I with the good XML is like we have this kind of like mechanical XML, right? If we can have we talk about other MTK and others, right? So the potential also can be standardized in some format, right? And XML could potentially one of them. Like we can kind of put in all way standardizing in one format XML. I think that throughout the end to end process, that would be really nice. I think like so that I think like they're more kind of like they may are interchangeable, right? Like this kind of like the hierarchical IO and things like that. If they can be reused of many of these things, even like the code or the algorithms for this kind of commands like NDD is like throughout different process of this like 3D design. I think that would be one plus to consider there. That's one point. Other point is just probably I think like I think this is probably more have a plus and con depends on in individual opinions. Like XML has more structure. I personally like that is like give it a lot more control in terms of the standard format, so it doesn't get divert too far away, or can they detect what other option can be read on other than just a free form. On the other hand, I think YAML is good. I think like it gives a lot of flexibility in that sense, but sometimes data can get really out of the bound, like because it get too much freedom without like more strict schema. So that's another point to consider. Like. That's just my 2 cents on that.
Mhm. Okay. So again, I will reach out to our JEDEC rep and make sure they don't have any, hard concerns with the YAML. But I think at this point, what I'm hearing is YAML is probably the way to go.
I would prefer personally. I would prefer like if do XML and ever kind of like transform into YAML. I mean, but it sounds like other people maybe more prefer, maybe majority more prefer YAML than it sounds like.
Yeah. Well, again, it's going to be the designers who are not hardcore software guys typically generating this data, so they're probably going to be a little bit more amenable to going YAML. That's kind of what I'm hearing.
Yeah, but I think generating data can be using the tools, right? Something like that way, right? Doesn't really need to know. I think like the underline as a format, right? So it can be some sort of UI or script to generate that. But I think like probably more like the person who build the tool itself will need to know about this format in order to make sure that it format it correctly that way.
Okay. Just another comment relating to these rules. We definitely need to be able to support, silicon type rules as well as organic, type rules. So I'm assuming, Zane, that this will accommodate both, substrates, organic interposers, fan out, as well as traditional silicon interposers and bridges. Correct?
Sorry, Tony, can you repeat that? I just missed.
Yeah. So it said for these rules, for your silicon assembly DRC rules. Actually, Rudy might have exception. Maybe we need to support non-silicon as well, but we want to be able to support silicon as well as organic interconnect. So silicon interposers and bridges, but also organic interposers and fan out. So those we need to be able to support those types of rules.
Yeah, it should be. I don't think there should be any limitation on that part. It should be fine.
Right. Now the other thing is we're describing a format for these rules. Eventually the checkers out there, the DRC checking will, those sign off decks need to be created. There is some work that's being done to be able to automate the ability to create those decks. Is that something we want to leave as an exercise to the EDA vendors, or is that something we want to look at in CDX?
Are you talking about the kind of rules?
Well, I'm saying to create, for example, a Caliber DRC deck or a Cadence DRC deck. I think that's probably something the respective EDA vendors would support.
Right, I'm thinking the same thing, Tony. Whether we put that in our official checking or embedded checking, there's umpteen ways to check these things. And
right.
Yeah, I think we'd want to just have a format that we could read, parse, and then we leave that to the EDA vendors for that implementation.
Yeah. Yeah,
Yep.
so I think in general, we want this format to be EDA neutral. But I think we also want to make sure that, you know, at least the participants in this, that, you know, we make sure the format can be readily supported by the industry checkers out there. So if we need
Right.
to,
As long as the format's described, I think we meet that as far
Yep.
as the EDA companies.
Yep.
And
Okay.
and then again, we're talking, just so I'm on the same page again, physical dimensional rules separately, the electrical or constraint.
I'm
electrical
talking
constraint.
physical.
Yep.
Yeah,
Yep.
the
Yep.
phys-
And just make sure
physical
I'm
stuff.
tracking. Yeah. All
Yep.
right.
Yeah,
We can talk
we'll
about
get
where
in-
we put that later. Yeah.
Yeah. I think the MDKs will get into a little more of the electrical stuff than mechanical, but yeah.
No,
But this
I'm
is the
tracking.
physical stuff. Yeah.
Yep. Just want to make
Okay.
sure I was tracking. Thank you, Tony.
Right, so let me kind of quickly run through one example, something, you know, how we would define something. The format building blocks will be starting out with like a polygon definition. So you just define it as like a geometry, probably similar to like what's being done right now in other formats. Then you have a cell or object definition. Then you have a placement, and then you define the geometric transform. I think the very last one is very important. That's something I think existing formats don't really consider because they are generally focused more on a single piece or single die or like single package. So that's something, you know, we will probably need to consider is how the different chiplets or whatever, you know, that you're putting in this your 3D assembly, how many different transformations we can have, and how they transform, and how if they're physically correct. Uh, like one example I have is like we used to work with a customer, not Intel, but we used to have a customer, and they were placing like a silicon on a package on a board, uh, and then in their design they didn't flip it correctly, so the whole thing was like mirrored when the final assembly came back. So when we start doing more 3D designs, the geometric transformation becomes very important. And this is like a quick just an example of a cell or object definition. So you can just look at it and see what it is. You know, defining it on, so the cell boundary is a rectangle, it's a 60 by 60. Then you create some metals, you create some polygons on your top and backside metals, and these represent different boundaries. So one could be like a sort boundary, one could be for like your full die size. And we can, you know, you can support how many that you need or how many you want. And then that kind of just, you know, you're just defining your cells as polygons. Okay. Moving forward, for the die file, same kind of idea is like define the definition, the edges, you know, the cell definitions, cell instantiations, the bump geometry, bump regions, and then the last one is backside and front side bumps. So as I mentioned earlier, that's becoming very important, how you define the backside and front side bumps. And then, you know, this ties back with the transformations is where you start running into some problems. Is you know, if you have a single die, like some companies like to split them up because it's just easier to design it that way. But then how do you combine your system together if you treat a single die with top bumps, bottom bumps? Like, are you going to support like all formats or all different variations of that? Are you going to ask people to always have like a die with bumps on both sides? So those are some of the considerations we'll have to take into account. And then the last slide, talking about a little bit more on the bump count side. So we, in our working model right now, what we have seen is basically we kind of split larger designs into 1 to 2 million bumps or 1 to 2 million pins. And that's kind of like the sweet spot for us, at least, to run the DRCs on. So if you have, like, let's say like a 10 by 10 part, and each of those cells have like 2 million bumps, right? We have seen is like when you split it up into like a region that's 1 to 2 million bumps, that allows us to run the DRCs and everything in the kind of like an optimal amount of time. And then we need to define the front side sections explicitly to go along with the bumps, front side and back side for the wafer. Some other foundries might have some different definitions. So just have to be careful on the format, on what's coming from Intel or what's coming from somebody else. So hopefully everybody can agree on using the same definition for that. And then the last kind of point is just be able to define different geometries. So not only like circles or squares, but also have like octagons or whatever other unique shapes there might be. Because so dies are more limited because everything is orthogonal in the silicon world, but for packages at least, or any kind of more interesting fan outs, you might end up with like oval shapes, or I don't know, some non-uniform shapes, like still like kind of circular, but not really. So we just need to be able to make sure we can support that. Right. So that's all I have.
Zane, a couple comments or questions. In some cases, the backside, TSV is done. It could be done by a separate vendor, right? So the back end of process. So, if it's obviously that information needs to be into the DRC rules that we're defining when you're going to assemble the package, but you've got a die and a GDS, but I guess there will be, typically for TSVs, for example, you just have a one-dimensional cell that's on the top and it comes out on the bottom. But how do we deal with that? To obviously where that bottom side thing needs to go, I guess needs to be defined in the GDS, but physically it's not in the GDS. It's done by the processing.
Right.
So how do we deal with that? Because I know when we talked about this at JEP, we said, is the die bumped or unbumped, right? Because the bumping could be done by the assembler as well as the TSV post processing.
Yeah, I don't know the answer to that question, but that would be an open also, is just to make sure.
Right at the end, maybe if I could get one in too, is again, like you talk about these non-Manhattan type shapes, or are you looking for something to, like Gerber can specify, curves and things differently than we can in GDS. So you're looking for something to modify that or allow translation between those two, for these bump geometries. So I guess what were you thinking there? Same.
I think you can probably just define it as a shape or a polygon.
Okay.
Wouldn't be. I mean, Gerber is going backwards, right? So Gerber would be.
Yeah, exactly. But I always come up to that, how they do some of the circular shapes over there versus the way we do it in GDS. That's all.
Well, if you look at like the Intel LGA, on the LGA side, it's it's very much, it's a polygon, but even the corners of the polygon around it, it's when you look at it, it's a very complex shape. It's just a pad, but it's a very complex shape. And I think that's what Zane's saying. You need to be able to support any shape, not just on the die side, but also on like the LGA side and stuff like that.
Okay. That's why I was asking what you're referring to. Well, okay. Thank you. And the high bump count, you mentioned that for DRCs. I'll take advantage of every second we can. You mentioned that for DRCs. Are you thinking that is a concern with some of the routing as well, or is it primarily for the DRCs and the DRC runs and getting that quick feedback?
For the DRCs, like just for the bump DRCs.
Yep. Okay.
Yeah, this is pre-routing.
Okay.
Before routing.
Just want to. All right. Thank you.
I think the commercial product name is like Foveros Direct. So I think if you Google that, you can see some of the information on it. But that's that's where we're seeing the high pin counts.
Okay, we're at the top of the hour. Any last questions or comments from the audience?
So sounds like we require a fiducial or something like map or something like that, right? To be able to, I think, identify the front, back, and those kind of different, and also location of the die, right? So I think when we, or identical die when we put that in the packaging and things like that. That's something a consideration. I think that what Jen you were pointing out earlier, right?
Yeah. Like you'll need fiducials, yes. We'll have that in our defined a little bit better in our spec. So I can, like I said, I don't know. We should have the spec out. I will let you know what the ETA is, but I don't know when exactly it will be out, but I can share that information when our full spec is released.
It sounds good. Looking forward to that. Like, yeah, thanks.
Okay, I just want to make one last statement here. 3D blocks is doing a lot of the stuff. What we're doing is independent of TSMC, so we want to be very sensitive not to on how we communicate this. So in the working group, we're working on a format. We're not looking to replace 3D blocks. I think our position as from an EDA vendor, and I believe Cadence is the same, is we are still supporting 3D blocks, and with these formats. I think the way we would support that once we adopt these is through translation. Now there are some issues and limitations with 3D blocks where maybe we can't translate. That is an issue with 3D blocks, but at least we want the format to be truly open source and driven by the industry. And there are some concerns with with TSMC, but we need to be very, very careful that we keep this internally, and we don't want to the message to get out that we're undermining TSMC or working with an alternative standard. So I'd like to make sure everyone is very sensitive to that.
Understandable. We should be very neutral that way then. It's just addition, not replacing anything, just additional.
Yeah. So we're creating ADKs, that's what we'll be communicating externally, and if you're interested in the details, join the group. Okay. Thanks,
Sounds
everyone.
good. Yeah, thanks. Yeah. By the way, I will putting all this what we talked about in last week into an Excel spreadsheet, and maybe we can start going to that way there, and everyone can start adding on it also. Just compiling the list there, putting in the XML, in the Excel sheet. Sorry.
Okay. Thank you.
All right. Yeah. Thanks, everyone. Bye.
Yep. Sure. Pratush, you want me to take this, or you want to? Yeah. So yeah, we have a short period of time, but I think we're trying to just summarize at a high level what we're bringing to the table. So workflows. So these are and by a workflow, these are putting together all the necessary tools to support the design and verification of these 3D HI designs. So at a high level, we're looking to go all the way from, high level modeling through detailed sign off and test. And to support the high level modeling, I think it is what we're offering here is predictive modeling. So this allows us to do some very early analysis, early in the design cycle, perhaps even pre-layout in many cases. So we can make some early decisions before we go off and make detailed decisions about how we're going to build and connect the chips. So we call this predictive analysis. And this includes signal, power integrity, thermal, mechanical stress. So we feel that's an important part of the process. As you start doing the design and doing the layouts and such, we want to be able to do in design. So we do the analysis and make the corrections as we're designing the circuits. And not waiting for everything to be done to do the final sign-off checks and find out you have to do redesign. So that's what we mean by in design. And then sign-off, actually, this is making sure that everything is sign-off quality to ready to go off to be manufactured. Another important component is the design kits. So we are driving standards in collaboration with Cadence and several other companies through the OCP, CDX, Chiplet Design Exchange is a working group, and we're looking to develop and drive some new standards to support 3D HI. We're looking at defining a material design kit and advanced assembly design rules, as well as all the other everything that is required. So it's a comprehensive set of design kits, everything that's required to support the design and analysis. And these will be open, machine readable formats wherever possible. And that, as I mentioned, is actively going on as we speak. And an important thing is really managing all this data. So, we're dealing with system data, we're dealing with chip data, manufacturing data, mechanical, and all these different design kits and third-party IP. It's a very, very complex endeavor to build these devices. So we believe data management is very important. So we have developing a system which we call IPLM, IP life cycle management. And this gives us the ability to not necessarily manage at the actual database level. So those specific designers will use revision control, whatever systems they have. But this is a layer that we build on top of those disk layers to kind of represent all of the data, IP data, the work in progress for the database, the package data as metadata. And then that metadata can be used and linked and create digital threads. So we can look at all the dependencies between the IP and we have full traceability. And then sitting on top of that, we can actually have a PLM system where you're developing a product where you could do traditional product lifecycle management, which gets a little bit more into kind of handing off a BOM to manufacturing and dealing with the overall program in terms of gated milestones for starting program, procurement of IP and such. So we think this is an important component also to tie all this stuff together. Questions or comments? Yeah, Hong Ben, just to add one thing, we also talked about, wasn't in our slide, but putting sensors on the dies so we can monitor stress, thermal analysis, possibly aging on the different structures, because that is, as you stack the die, you don't have direct access to some of that information. So we do want to be able to model that and actually have IP on there, which we can calibrate on each of the die standalone. But when you put them in the stack, you don't have access to that information. So having calibrated sensors in the stack gives us the ability to measure the data and see how well our sign-off checks are doing for the 3D stack. And if we need to adapt our flows and models, gives us the ability to provide that indirect access to that information. Yeah, absolutely. Hey, British. Yeah, why don't you just pull it up? Yeah. I did not get a chance to look at it. Oh, no, that's your job. And when in doubt, send it, if you know. You're talking about ASU? Yeah. Okay. Mm-hmm. Yep. Yep. Very good. Mm-hmm. What did we define InDesign someplace? I think we should do it. So InDesign analysis, what we're calling it, enables the physical design team, the design teams, right? The design teams. I was going to say to interactively run checks during the design process. During the design process, right? And to make the changes, No, it does. It does. And design analysis will enable design teams to interactively run checks during the design process and correct them in real time, or and addressed issues or rather than waiting to run the sign-off tools once the entire design is complete. Yeah, the sign-off flow to be run on the completed design. I think people know what sign off is, right? Okay. Yep. Okay. And let's see the integration of tools. I'm just reading the last 3D cable. Do we want to summarize the multi-domain data management? Yeah. So I would say, design kits is a sub bullet. No, we could do it as a sub bullet. Design kits, 3D 3D AD design kits, right? Does well, so it's the design kits, it's the IP. Yeah, you could say design kits, IP. Yep. Yeah, it is the design. I call it design WIP, design work in progress, and design scripts. So we're managing the IP, the work in progress. Yeah, the workflow scripts. Yeah, what does environment mean? It's not jumping out at me. The critical design verification. All right. Let's do a couple bullets. So the first one is design kits, design IP, and the design. You can say the design the design data. Yeah, carriage return. Right. and then there's the ver yeah, well, we talked about VCP, verification capture points. That's a little, I don't know if that's defined someplace, but we're well, I'm trying to say we're why don't we say design and verification data in the first line. Design and verification data. And then this is digital threading. Then we can say, I mean, that's one of the values. So we can say